Okay, welcome everyone. This is the second day. So today we're going to start with a topic that wasn't really touched on yesterday, but which is an important topic in learning. That is online learning. And Sasha will be the next up with
Thanks. Thank you for the invitation. Pleasure to be here. I'm going to talk about work with Dylan Foster and Karthik Sridharan on sufficient statistics for online prediction problems. The talk will have 4 parts. I will start by motivating the problem. That's the problem that comes out of online learning. I will then go into the Burkholder method, which is something about martingales and has, if you don't care about learning at all, you can just, look at that part, listen to that part. I will then go back to online learning and define sufficient statistics and show how the Burkholder method can be applied to the problem of online learning. And then the last part will be kind of a hunt for these Burkholder functions, which are potential functions, Lyapunov functions if you wish, and we'll give a result for matrix prediction in that context. Okay, so let me start with the motivation. A very general goal is to eliminate this middle step where typically you write down a stochastic model, you get data, you estimate the model, and then you make a prediction. But if the prediction is your goal, then the question is whether one can avoid putting down stochastic assumptions about that model, the process generating the data, and then go directly to prediction like that. Okay, so here's an example. It's a very simple example, so I usually start with this example. There is a matrix of users and movies, and at every time step, you're being asked to predict plus or minus 1. Luke, is that plus 1 or minus 1?
It's plus 1.
It's a plus 1. And Luke is correct, so there is no mistake at this point. But then, how about this one? Minus 1. Have you seen my slides? So, indeed, that was a minus 1. Very good. Now, the question is, can one fill this matrix one by one and have a small number of errors, just as Luke did right now? Okay, so now we have to model the problem, and so. If you're a statistician, you would say, okay, what I observe are some kind of noisy version of some low-rank structure or low trace norm structure, right? That's a typical assumption. I see IID observations of this, and then let me try to estimate this underlying signal, right? That would be the statistical approach. There is a different approach, which I will show in a second, which is let's not make assumptions about the way that data are generated, but let's still hope that there is a low rank or low trace norm explanation at the end of the day of these data. Let's hope that that's the case. But somehow, let's make it so that if there is a low rank explanation of these data at the end of the day, Luke should have made no mistakes, or very little, as he did. And if it's not true, if it cannot be at the end of the day approximated by a low rank matrix, then we actually don't care how Luke was presented. He could have done a large number of mistakes, right? So that's the idea. Let me make it more mathematically precise. The protocol is that for n iterations, we observe some side information xt. That's an element in some abstract space x. For matrix prediction, it's just the coordinates of the user-movie pair. That's the side information. Then we make the prediction y hat t. Let's say it's in the interval minus 1, 1, or you can force it to be thumbs up, thumbs down. And then you observe an outcome yt in the same space, a real valued outcome. Okay, so what's the goal? The goal is to have, for any sequence of x's and y's, and so for those in this business of online learning, this is very trivial, but I just want to make sure that everyone is on the same page. What I want is not in expectation over sequences are under the model, but for any sequence, that the error that we make, the number of mistakes that we make, right, the y hat t minus yt, and we can put a different loss function there, is small if the sequence is nice in some sense. And the question is, what does it mean for a sequence to be nice? Well, let's write down some function phi of the sequence. That's our modeling choice. And this function should be small somehow on sequences where at the end of the day, the matrix is indeed low rank, or close to being low rank, and large on other sequences, right? That would be the goal. And it's not clear that one can do this, and it's not clear what is the space of these functions phi for which this is possible, right? So once you write down the phi, it's clear that it's either possible, that there exists a prediction strategy such that for all sequences this holds, or it's not possible, right? It's a dichotomy. And we have very little kind of understanding of which functions phi are achievable in this way, and we'll show some steps towards that question. This is a typical way of a typical phi that we at least can work with, or we have some idea how to work with. You can think of this as finalizing the x-y relationship. So instead of requiring that there is a linear model that y is equal approximately w times xt, at every yt is w times xt, instead of making that as a stochastic assumption, we'll lift it into a penalty and say, well, the number of mistakes should be bounded by how well a linear explanation works for y from x. And then there is some penalty for the x's, right? So you can think of a distributional assumption as a distribution on the y given x, and as well as distribution on the marginal of x. And that's kind of an additive form of such a penalty. Okay? Again, for those in online prediction, this is trivial, but I want to make sure that everyone is on the same page. Okay, any questions about this, the problem? So the question is, how would you do this? How would you develop this strategy for predicting y hats such that you keep this this goal, that for any sequence this works? And it's not hard to see that this is just like a huge dynamic program, if you wish. Some kind of it has some kind of recursive structure that will come out from using a potential function for these methods. Now, let me just say that if Cn is data independent, it does not depend on the x's. This is like the distribution-free learning and statistical learning. Then we have a full characterization up to a factor 2 of which C's are possible and which C's are impossible, right? So we have the characterization of the smallest C for which this would be achievable. This goal would be achievable. So let's go back to matrix completion. As I mentioned before, xt in this case is just the indicator matrix, 0 everywhere except for the place where you need to make the prediction. Okay. So that's a 0, 1 matrix with just 1, 1. If we write capital letters for the matrices, if W is some matrix of ratings, then W times xt is pulling out that entry, right? IT, JT entry. And then we compare that with YT. So you see that this is exactly how well the best matrix in the set explains your observations, right? And if indeed these ratings are exactly coming out of a low rank matrix, then this would be 0. And if it's proximate, there is a slow, smooth degradation. What kind of set F should we take? Well, as I mentioned before, everyone believes that there is some kind of low rank structure because people are not too different. So we can relax it to say that this is a tau nuclear norm ball, let's just cap the values at point-wise as well. Right? So that's a possible set that we can take. Now, if we want to include rank R matrices, the radius of this ball should be something like square root of rank times the dimension of the matrix and the other dimension of the matrix, p times n, right? And that's important to keep in mind for the next slide. Any questions about this? Okay, so at this point, it seems like this modeling choice for that function phi is a good choice, right? It has two components. One penalizes how well the linear model does on explaining y from x. And there is a penalty, which we, as I mentioned, we know we have a full characterization of this. But unfortunately, in this setup, if you put in the radius and you put in all the numbers, you get a order of n. This data-independent quantity is order of n. So you don't get anything essentially, right? The result is vacuous, because if you have this value at order of n, the whole thing is order of n at most, right? So you don't get anything. There is hope that if you make Cn data dependent, that you can somehow avoid this. So we need to differentiate easy x's and hard x's, and hopefully tilt the function c in such a way that we still get something meaningful and nice presentation of the x's, and something vacuous on the bad presentation of x's. Right? So this is a fully deterministic setting. I just want to draw your attention to the fact that there is no probability anywhere. It's a completely deterministic setting. Predictions are deterministic because it's an absolute loss, although you could have a randomized strategy. There is no probability on the sequences. It's fully deterministic. Right? Questions? Do you have a question?
Some question so here you observe DW scalarity.
You observe xt, which is just the location of where you need to make the prediction. Then you make a prediction, you observe the outcome, and then you move to the next step.
What is the difference? So small xt and big xt?
No, it's just a, sorry. So this is just a matrix. I just capitalize it because it's a matrix.
But then you observe big xt?
Yes, yes. You observe where you need to, so someone tells you where you need to make the prediction.
But it's a matrix. You observe all the matrix.
It's a zero everywhere, except for one location, right? It's this outer product.
All right, sorry. Thank you.
Yeah, please stop me if there is some question. Okay, so the question is, can we make this data dependent, right? That's the bottom line. Because the reason that data independent penalty doesn't work is because there are some sequences of presentation which are too spiky, in which case you don't get any good performance, which makes sense. Like if someone keeps asking you to predict the entry 1-1 for this person in that movie, then you can't really do anything for the rest of the matrix, right? And so it makes sense that we need some kind of extrapolation that hopefully is nice if there is something like a uniform or close to uniform sampling of the matrix, right? And again, this is completely deterministic. There is no process, stochastic process governing this. So okay, we can turn to these books or more books, and kind of the suggestion would be to use convex optimization, online convex optimization, and I'm going to argue that this is not going to work. So why? What would such a result look like? I'm switching back to lowercase. It doesn't matter in this case. It doesn't matter. If you force yourself to output predictions based on your own update of WT, so you can imagine that you keep updating the matrix WT, and you output that entry for the matrix, right? That's one algorithm. That's called proper learning, and then y hat t is just this product. Okay. In that case, you can write this as a ft of WT, and this is ft of W. And this is a convex function of W. And we know these online convex optimization methods. The typical method is a gradient descent. WT plus 1 is WT minus the gradient step. And if you want a different geometry, we know that we have to use a map to this mirror space, to the space of gradients, and that's realized by taking some strongly convex function with respect to a norm, and this defines the usual mirror descent. Okay, and in particular, exponential weights is just using this map, which is strongly convex with respect to L1 norm on the simplex. Okay, so what do you get with the gradient descent or mirror descent? Well, what you get is something like square root of n, typically. If you unpack what that square root of n is, and you use an adaptive step size, like ADEGRAD, you would get something like square root of the sum of the norms of the gradients of these functions. That's the rate of conversions that you get. And because our functions are just absolute value of wx minus y, the gradient with respect to w is just x. Okay, so that gives you a norm of x squared. So it gives you square root of the sum of the norms squared. Any questions about this? So the question is, can we use this as a data-dependent quantity? And you see that we can't because, well, so what is this norm? It's a norm on the matrix, and we have a trace norm. Well, this is actually the dual norm for the trace norm, for the nuclear norm. So this is a spectral norm wall, a spectral norm. And in fact, any norm you take, this is the indicator matrix, that's going to be 1. So this is always 1, and you have square root of n, right? Irrespectively of the x's. So we haven't done anything in this case. Now, jumping ahead of myself, it would be nice if we could, instead of this, if we could get this type of bound. So that's a nuclear norm, spectral norm, operator norm, of the sum of xt transpose, max with norm of sum of xt transpose xt, right? So instead of sum of square root of the sum of the norm squared, this is the norm of the square, right? It has the right units, right? It's just you take the norm of the sum of the squares instead of sum of the norm squares, right? Now this is going to give us, towards the end of the talk, I will show that this gives a non-vacuous balance. Why? Because xt is an indicator. xt transpose will put it on a diagonal, right, at the it location, and this puts it on the jt location. When you're adding them up, you're just going to get the diagonal. The spectral norm will be just the maximum on the diagonal. And so that exactly gives you the kind of spread outness of the sampling of the the it, jt entries, right? Again, it doesn't say anything about the stochastic nature of this problem. It's fully deterministic. The problem is deterministic, but it does what we want.
Isn't it still n?
It's not n, because if the dimensions are like p by p, let's just say it's a square, just for simplicity, right? Then it's n over p. You would expect n over p to be the max, and so if you plug in the numbers, it gives a.
You want to divide by. You want to divide by.
Yes. Yeah, I'll give the exact. Okay. So now you can ask why this form, and the answer is because of matrix concentration inequality. So this is the term that comes out in, like, if you look at TROP or matrix concentration or matrix Kinchin inequalities. This is the term. So at this point, you should be wondering why the heck are you talking about matrix concentration? There is no probability. There is no stochasticity here. Nothing, right? So what makes you think that this should be possible? And what makes it think that this is possible is the strong connection between martingales and online prediction, which I will outline next. Actually, in the third part. Okay, so at the higher level, the gradient descent is not working because it's not keeping the right statistics. That's the word in the title of the talk. It's not keeping the right statistics about the sequence. We need some other method. The gradient descent or mirror descent will not work here. So the question is, can we go beyond the notions of smoothness and strong convexity, which is what is being used by mirror descent? And we would be searching in the dark for a method, right? It's not clear how to develop this prediction strategy, but there are some connections that we've been developing for the last 10 years that connect online prediction to martingale inequalities, and this connection goes through von Neumann minimax theorem. And this started with the work with Peter in 2007, 2008. And what I will present now is a connection between martingale inequalities and geometry, or existence of these special Lyapunov-like functions through the Burkholder method. And then we will go back and use these Burkholder functions for online prediction. So that's the overall goal. Okay, so let me describe the Burkholder method, which is, I think, it's very neat and not many people know it. If you want to know more, please look at this book, Sharp Martingale, Semi-Martingale Inequalities, by Adam Osikowski. He's the expert on this method. So if you didn't pay attention up to this point, and you don't care about learning or prediction, but you care about probability, you can start from a fresh point, fresh start. Okay, so epsilon 1, epsilon 2, epsilon t, and so forth will be IID Rademacher random variables. And we define a dyadic filtration, dt, which is just a sigma algebra with up to t. X1 and so forth will now be a martingale difference sequence with for this filtration, right? Adapted to this filtration. And so expectation of xt given up to t minus 1 is 0. Okay? Good. Now, because it's a dyadic filtration, at every time step there are only two possibilities, right? Depending on whether epsilon t is plus 1 or minus 1. And they have to add up to 0. Right? So you can always write any dyadic martingale as epsilon t times some predictable function, right? So this is a predictable given the past, right? Times epsilon t. So I will sometimes write it like this, but sometimes I will write it in this form, and it should be easy to switch. Any questions about this setup? Genetic? Okay. All right, so suppose that for all, let's say dyadic, it's not important, it's just for simplicity. Let's say for all dyadic martingale different sequences and all n, you can prove some martingale inequality. This is a very generic martingale inequality. Pretty much anything can be written in this form. It's the expected some function v of x1 through xn less than 0. Okay. And here I'm going to overload the notation and take v, the domain of v to be sequences of different lengths. Okay, so I don't have to put an extra symbol. Okay, good. Now let's take this v. So suppose you can prove that inequality. Right? Maybe Dub's inequality or Burkholder-Davis-Gundy inequality or whatever. Let's take that inequality and let's check this condition. So what is this condition? This condition says that if you put any deterministic sequence x1 through xn minus 1, take any deterministic xn, but then the only randomness will be this coin flip. Then there is a certain concavity-like, it's not really concavity, but essentially you can erase this last guy, right? It's going to be upper bounded by v of a sequence up to n minus 1.
You're assuming this holds?
Check. Check if this holds. Just check if this holds. If it doesn't hold, then you can improve this inequality. So that seems like an amazing statement to me. You just check some property of v, and if it doesn't hold, then there is a stronger version of this inequality. Another way to say it is the extremal functions for this inequality have this concavity properties. So if you've proved something, but the concavity doesn't hold, concavity in quotes, okay, it's not really concavity, then there is a stronger function u, an upper bound on v, at least on some point in the domain, for which you can still prove this inequality. Right? Any questions about this? It's a very simple statement. or a claim. That's a claim.
Well, why do you say it's strengthened?
It's strengthened because you're going to prove it for some u, which is a strict upper bound on v, but you're still going to prove that expected u less than 0.
But u should be, I mean, u or 0 should be, or that's stronger.
No, it has to be upper bound on v. Right, so if you prove that inequality for some v, and for all n, and for all n and for all martingale different sequences, if it doesn't satisfy this, then there is a way to get something stronger. Okay, let me give an example. Let me give an example. So take this function v of x1 through xn, x sum of xt minus xt squared over 2. Now let's check this restricted concavity. So the last guy has the epsilon, right? And so, of course, when you write it out, the last guy is the only right choice. Then you use the usual inequality that gets x squared over 2. That cancels with the xn squared over 2, and you get x up to n minus 1, which is the v function up to n minus 1, right? So this should be trivial, right? So it does satisfy this condition, and so at least the claim doesn't say anything about this case, right? For all we know, this is the extremal function. You can't improve it, okay? But here's another one. Take v, now not real valued, but vector valued, x's, and take the norm minus some constant square root of the sum of the squares of the norms. Okay? If it's Euclidean, you can take 2. In some other spaces, you might have to take some other k. But this doesn't obviously satisfy any, doesn't satisfy this inequality. Right? And so there's a strengthening. There's a strengthening of this inequality that still holds. So there is an upper bound on this. There's some u which is larger than this, for which you can still show that martingale. Yes.
You're assuming v is negative.
Second?
You're assuming expected value v is negative.
Yes. I'm just writing, so any martingale inequality, you can massage it into this form. Okay, I don't know if it's any, but maybe.
Because these are positive. These are on the next side are positive. So how do you say?
Oh, sorry, I should take a log, I guess. Oh, yeah, sorry.
So somebody's and then u being bigger than v.
Sorry. So sorry, I should subtract 1. I apologize. Yeah. So this should be minus 1. Okay. Minus 1, and here, everything is correct.
But then u has to be less than v because they are negative.
No, so this is with a minus 1.
Yeah.
And then there is a u which is an upper bound on this first.
Oh, okay.
But in this case, there isn't because it's already satisfied. Right? Yes, sorry, there is minus 1 here. Okay, good. So here's another way to write it. It's the same idea. It's just a restatement. If you can prove a martingale inequality of this form for all martingales, then martingale different sequences, then for any dyadic martingale different sequence, then there exists a function u, which is the strengthening, such that u is an upper bound on v for all t and pointwise. U of the empty set is less than 0, right? Because you kill one coordinate at a time, right? And this concavity property holds. Right? That's the same thing that I said. It has both directions now. Because if you know that there exists a function of this type, then it's clear that you should be able to prove that martingale inequality, right? Because you start, here's the proof, right? You start with expected v. Now you have a pointwise up strengthening to u. Then you use the concavity property to erase the last guy, and then the next to last guy, and so forth. And then you end up with u of empty set, and that's by assumption less than 0, right? So think of u as like a Lyapunov function or a driver that lets you prove a martingale inequality. And essentially what this is saying is, if you're able to prove a martingale inequality, then there is a proof of this martingale inequality which goes in this recursive manner, which is a non-trivial statement, right? There must be a proof of this inequality through some function u, which involves this dynamic programming type of, backward going backwards. So, of course, the question is, how do we know that it exists? And the proof of existence is actually very simple. You can define u star on any sequence x1 through xt as a supremum over random continuations xt plus 1 xn. Right? So it's a supremum over both n and martingale different sequences. That this is not a deterministic sequence. This is a random continuation, right? A martingale different sequence. I should say this is the law of the martingale different sequence, and then you take the expectation, right? And the claim is that this u star satisfies the three properties. So this is a strengthening.
Why do you have this super? Isn't each super n bigger than e? Because there's no the x is not free anymore, right?
So these are not, but these are. So it's a supreme over the law of the continuation.
But isn't the expectation take this out?
Yep. And that's why you get the function of x1 through xt.
Correct.
So one question?
Yes.
And here, the supreme is over all martingale differences.
Yes. So if you restrict to that over distributions, yes, over distributions. If we restrict to dyadic, then just the dyadic.
Ah.
Good. In fact, you can show, I'm running out of time, so you can show that u star is the smallest function set that satisfies these properties. Right? Okay, so some examples. This is close to the example that I showed before, but instead of norm, it's norm squared. This is known as a Nemirovsky inequality. The martingale inequality is that the expected norm squared of the sum is upper bounded by some constant times expected sum of the norm squared, right? Of course, if it's Euclidean, k is equal to 1, and this is equality, more generally, you can hope to find some k. Right? So what is the v? The v function is, it's a function of the sequence, and I'm already foreshadowing the sufficient statistics. So it's a function of the sum and a function of the sum of the squares of the norms. And it's just this difference, right? Because you want to show that this holds, so you can show that expected of left minus the right-hand side is less than 0, right? So it has that form of expected v is less than 0. So it turns out that, okay, you can verify some property of this u star that you construct optimally. And then this restricted concavity boils down to the following inequality. Because of lack of time, let me just give the punchline. It turns out that this map from x to u star, which we will call the Burkholder function, any function that satisfies those three properties we'll call a Burkholder function. So this map is smooth with respect to the norm, and therefore its dual is strongly convex. And that's exactly what we need for mirror descent. So there is a certain sense in which this martingale inequality is the reincarnation of gradient descent or mirror descent, because the Burkholder function captures the necessary geometry for that problem. Okay, and the claim is that we need to do something else for that matrix, for the norm of the sum of the outer products of the matrix. Okay. This is inequality that I showed before. Again, the expected norm minus the expected square root of the sum of the squares is the inequality that we want to prove. This is the function v. And here I will just give you, for real values or for Hilbert space, this is the actual u function. I believe this is the optimal u function, right? You can look in chapter 9, I think, of Adam Osikovsky, that book, and you will see that this function. It's not an obvious function, but it's not difficult. Well, again, it's relatively easy to construct. This actually gives the adaptive gradient descent, adegrad.
In what sense does it give adegrad?
Because it has this property, and now if you try to find the optimal way to move, it's exactly the step in the like adaptive gradient. It actually gives a bit stronger.
Maybe I missed it, but sorry. Where is the algorithm coming from you?
Not yet. Yes, that will be the last part. I'll come to that. Okay, let me skip this one. Yeah, so sometimes this is the Burkholder function. It's not convex, not concave, but it has a certain restricted convexity properties. Okay, so now we talked about this connection. So I outlined the connection between martingale inequalities, and we call it geometry because this function, the Burkholder function, somehow encapsulates the necessary geometry for the problem. Now I want to explain this connection between online prediction and martingale inequalities, which is probably better known. And let me also discuss the sufficient statistics. Okay, so let me remind you that the goal, and here I'm writing a genetic loss function. Think of this as an absolute loss if you want. We want that there exists a strategy such that for any sequence, the sum of the mistakes that you insert is upper bounded by this function phi per sequence, right? That's what we want to have. If we go back for inspiration to statistics, sufficient statistics are defined with respect to a probabilistic model. Right? Once you write down the model, you can talk about sufficient statistics. Here we don't have a model, so sufficient statistics can only be based on this function phi, right? That's our only modeling choice, this function phi. So here it is. We say this is a definition. We're not claiming that this is the only definition or the right definition. We're going to say that certain sufficient statistics, certain functions are sufficient statistics if we can replace this goal with this goal. So let me try to unpack it. We're going to say that there is some vector space T and a function that maps from the x, y reals into this space of sufficient statistics. And it's going to be an additive sufficient statistic. If there is a function v such that point-wise, so think of this not as a strategy, but just point-wise. You plug in values for x's and y's and the y hats. And point-wise, you can upper bound this by v of a sum of some function t of xt, y hat t. This is the side information. This is our prediction. And this is the derivative or subderivative of the loss function with respect to the first coordinate evaluated at the first coordinate, right? So this will appear. Think of this as just encapsulating enough information about the y, right? So you typically would have x, t, y hat t, and yt. We actually don't need the yt. It's better to just have the gradient for various technical reasons. So if this holds per sequence, like point-wise, then we'll say that it's a sufficient statistic. Right? Okay? Questions?
Don't you need something else? Because say the loss is bounded and phi is positive, and you could just set t to be, say, 1. Right? And it would be n and v the identity, and then you look at the left-hand side is bounded by n.
So once you fixed phi, now you can ask what is the sufficient statistics. And typically, so think of phi as the minimum over some set plus some penalty. Then the way that we do it is we expand the loss, because it's convex loss function, I should say that, and you get this right-hand side. Okay. Let me, for simplicity, assume that this map alpha to v of tau plus the sufficient statistic with the last coordinate, the subderivative being alpha, is convex in alpha. and the loss is convex in one Lipschitz. This is just the simplicity of presentation. Okay? Then we can restrict ourselves to deterministic algorithms. Okay, so where do martingales emerge? This is the question probably that is on the mind of many people, because there is this world of online prediction which is fully deterministic, and then I talked about this world of martingale, which is stochastic processes, and now we need to connect the two. So it turns out that if you write if this is the goal, you can try to write it as a max over x1, min over y hat 1, max over y1, and then second round, max over x2, min over y hat 2, max over y2. This horrendous min-max problem. Okay, so in the spirit of Wald, you can write down the min-max formulation of this, and if you can prove that game, if you wish, in the optimum sense, is less than 0, then there must exist a strategy that makes it possible to do this, right? So that's what we're doing, where we're saying max xt on the round t, min over our prediction, and then max over the outcome. And all of these are in the correct respective sets. I'm just not writing it down. And now this operator is, think of this as an operator applied to a function of, 3m variables, or maybe even more variables, right? Every time you apply this operator, you get fewer variables left, right? When you apply it one by one to this function, if you can show that this is less than 0, then you're done, because you've shown that there must exist a minimum, a choice for the minimum. And now, if we use the minimax theorem, this is what we did with Peter 10 years ago. If you do the swap, you go from min-max to max-min by von Neumann minimax theorem. But before doing that, you need to go to the mixed strategies over y, because otherwise this is not convex or concave in the right way. So once you linearize it and you do expectation of yt from pt, now this is linear in pt, and now you can do the swap. And that's why some stochasticity emerges. It emerges in the dual, in the von Neumann minimax dual. It's still not a martingale. So how do we get a martingale? Well, think of choosing a particular strategy, y hat t, which is the best response to the distribution pt. And we're going to assume that the loss function has a minimum for any distribution pt. It has a minimum in the set where you can do the prediction, right? Otherwise, you need to do the projection. Well, if you do that, you see that this is a martingale difference now, because if y hat star is the argument of the expected loss, so the derivative of the expected loss is 0, then any random draw yt from this distribution gives you a random subgradient which in expectation is 0, right? That's the usual trick of swapping expectation and the gradient, or expectation and the derivative, right? So this best response to the in the dual to the strategy of the adversary gives you that these subgradients, subderivatives are is a martingale difference sequence. And then you massage it a little bit more, and you can get it to be just a dyadic. And it's exactly of this form. And guess what? This is exactly the expected v, right? That we want to show it's less than 0, right? And moreover, it has the structure. It has inside it has the structure. It's not just v of the sequence. It's v of the sufficient statistics. So we started with sufficient statistics by expanding our goal. That leads to a martingale inequality in terms of these sufficient statistics. And now, when we go back to that Burkholder method, it gives you an existence of a potential function which is only based on these statistics. Right? Any questions? Yes.
So,
probabilistic setting, you think of sufficient statistics as not losing any information. Right. But here you just have an upper bound. It's like good enough statistics.
That's right. So if for it's not a general statement, but for many cases, you can write a lower bound in this form as well. You linearize the loss, pick a particular distribution for the y's, and that gives you a lower bound of the same form. It's quite general. It's not always the case, but
can you characterize when they're really sufficient, when they really have all the information?
I don't have a crisp characterization at the moment. I think that can be worked out. We didn't put too much. I'm not sure if it's going to be a nice condition or not, but you can write that. Okay, so there are two lemmas. The first one says that suppose that this pair T and V is a sufficient statistic, then the prediction strategy, and for V, as Peter is saying, it's going to be for V, the prediction strategy for V, so that's an upper bound on what we want, exists if and only if this martingale inequality holds, right? So that's the connection between prediction and martingales, right? You can get a strategy in this fully deterministic world if and only if this martingale inequality holds. And the second lemma says that this martingale inequality holds if and only if there is a potential function that will has these properties, right? So so let me say we all know that the potential method is kind of the right thing in the online world, right? We know that faced with a new problem, we need to look for this potential function. Hopefully, it upper bounds the difference. The difference in the potential function upper bounds the loss, right? This is an old history of this approach. But this pins down the types of potentials that we need. We just need to check this one property, essentially. It restricts the search for these potential functions to these Burkholder functions which have this property. Okay, so there is a universal algorithm, the Burkholder algorithm that we define, and it's just this. So once you've got your sufficient statistics, these are the sufficient statistics you've calculated up to time t minus 1, and the algorithm is just min-max of this, and if the max is over two possibilities, plus and minus 1, then this is very efficient. Okay, so that's the kind of the universal algorithm. In some sense, it says that if the inequality is possible in this online prediction setting, and you can expand it into sufficient statistics, then there will always be an algorithm of this form.
Is that for Burkholder U? Is that like a minimax for that V?
It's a minimax for that V, yes. For that U, not for V. So U is a strengthening of V. Okay, so now we have to hunt for these Burkholder functions. And let's do the matrix completion setting. So let me define the Hermitian dilation of X as the usual Hermitian dilation, and this is the square. And this is the goal, right? So don't look at this now. The goal is to have the small number of mistakes, right? And this is what Luke was trying to do. He was trying to solve this problem. He was trying to minimize the number of mistakes, and in particular, he wanted to ensure that the number of mistakes that he was making is no more than the number of mistakes made by a tau nuclear norm matrix, plus a penalty. And I mentioned that this penalty should be the square root of the norm of the sum of the products of matrices rather than the usual gradient descent. Right? Now, getting sufficient statistics is actually super easy. It's not something that's complicated. It's really routine. So all you do is you expand the loss. You use convexity of the loss. That gives you these gradients. Just expand it, right? Use the subgradient. And you see that these three are the sufficient statistics. This is like a one-line proof, right? So we know what the sufficient statistics are, and once you write the sufficient statistics, you can immediately write the V function in terms of those sufficient statistics. So we represent our goal as V applied to sum of T's. So what is V? It's lambda 1 of H minus, okay, so I didn't say what eta is. There is one more trick that you do, and that's square root is a bit annoying. And the trick is to write it as eta times the norm plus 1 over eta, right? And then tune eta using some other method, such as doubling trig or something like that. So you see that the eta is a step size. And step size actually is not there in the problem. When you start with the problem, step size is not there. It's exactly a choice that you introduce to make the problem easier, and that leads to gradient descent, for instance, methods that make easier updates. So you can work with this one, but it's easier to work with this representation and tune eta. Right? And that's where step size appears in gradient descent. Okay, so once you write it this way, now you can see that it's just lambda 1, right? Of this becomes, once you expand it, it becomes the dual norm of the trace, the comparator. Now that becomes just the h minus h squared coming from here, and that's it. And so then it's just softmax on that v function, and you can show that this function is a Burkholder function. Right, so we replace the lambda 1 with low trace exponential using the Lieb concavity theorem, and this is a Burkholder function. It's almost mechanical now. We start with a v. We start with our goal. We expand it. We write it in terms of sufficient statistics. We find the t and the v, and then we get the Burkholder function. And again, because you just need to check this concavity property, it simplifies the search of the potential functions greatly simplified. Okay. Now, once you have this u function, you can ask what are the corresponding martingale inequality. Actually, we didn't write the martingale inequality for the u. I'm going to write the martingale inequality for the v, and it's exactly what you can find in Trop and Mackey and so forth. Actually, maybe there are some cases I think this is more general. Okay. As I mentioned, this max of these two terms, which is exactly the so you expand the spectral norm of the Hermitian dilation squared into max of these two parts. And that is just the maximum of occurrence of any row or any column, right? So if you have uniform sampling, as we were mentioning, then you would expect the maximum to be roughly n over p, as we were discussing in the beginning. And the tau is square root of r times p. I'm just taking the square matrix for simplicity. Then you see that for this method, already after roughly n equals to rp observations, it becomes non-trivial. So if the sampling is indeed roughly spread out, in the sense that it keeps this diagonal XX transpose roughly balanced, then the result becomes non-trivial already after n equals to rp. P is the size of the number of rows, let's say. So rank times the number of rows is enough to get a kind of a non-trivial. Right? But if the sampling is really worst case, if these x's are just in one point, it's very imbalanced, then essentially we're not going to get any result. We're going to get n and then rp squared. So you need to observe the whole matrix before you start making non-trivial predictions. Of course, this is not what you want. Right? So the advantage of this is that we have no stochastic assumptions on the sequence. right? It's fully adaptive. At the end of the day, you look, you say, how balanced the sampling was. And if it was balanced, you've got a great, you've predicted well. There's a guarantee. And if it's not balanced, well, then you got some result. But it's really robust. It doesn't rely on these stochastic assumptions, which are in practice difficult to verify. Right? There is nothing about IID. It only depends on the sum. So the order in which these x's come makes no difference. Right? This does not depend on the order of presentation. Okay, so hopefully I've convinced you that there is an interesting set of connections between online prediction, which is a fully deterministic set of results that should hold for all sequences, martingale inequalities, and this connection comes out of minimax, one-over minimax. And then there's this new connection that we've discovered that exists between the martingale inequalities and existence of these potential functions, or Lyapunov functions, if you wish. And then we can go back and use that for prediction. So these are the contributions. We've defined some notion of sufficient statistics and the universal Burkholder algorithm for that. There are many open questions, so we only talked about linear f, classes of linear functions. Extending this to nonlinear seems difficult, but that's an interesting direction. You can imagine that if you have f that can be expanded in some basis, even though it's nonlinear functions, if you can have some representation in some basis, maybe you can extend some of these results. That would be great. Analogs for partial information problems, what are the sufficient statistics there? That's much more complicated. Analogs for problems with state and reinforcement learning, whether some of these, you can view this as a Bellman inequality or Bellman method, whether that can be extended to reinforcement learning. This is a very specific one. So I think that's it. Thanks.
Questions?
Yes. So you said that this is can be made entirely mechanistic, but there is one step that doesn't look so trivial, right? So
finding u, which is upper bound.
And you can verify whether this is all of it, how to improve.
Yeah, so I mean, you start with V, and we've done it on many examples actually. You start with V. You know that one condition that you need to check is concavity. And I mean, in many cases, you can start building upper bounds in such a way that it ends up being satisfied. Yeah. So I agree that, I don't think we can just have a machine in which we put it in, unless we phrase it as a sum of squares and then put it in a huge SDP, and then that spits out a potential function, right? But I think it really narrows down the search for these potential functions to just the ones that have this property.
So going back to Peter, is it using only the linear loss? So the linear loss is constants.
Linear loss meaning
so when you actually get sufficient statistics. So what are the examples when you know these are actually sufficient statistics in the sense of?
Yeah, right. So let's see. So there are examples, for instance, with square loss, where you just expand it out, and you can verify that the result is a U function that satisfies. You don't need to do any upper bounds. So that's one example. Another example is when you have, let's say, absolute loss, and then you can create a lower bound just by linearization type of argument that is like the upper bound. In the updated version on archive, there is a result that general enough.
Okay, thanks again.
Thanks.